All right. Hello, everybody. Welcome to the Grit City Think and Drink. Woo! That's right. We don't get to celebrate Tuesdays very often, so this is the way we do it. How many people are new to the Grit City Think and Drink? All right, lots of newbies. For those of you who've been here before, we all know that the newbies buy the beer for everybody else. So we're always happy to have new people, and you can invite people next time. Absolutely. Just so you know, I'll give you a rundown on the thing. My name's Jim Gall. I'm the host of the Grit City Think and Drink. I'm faculty at UW Tacoma. We do this the second Tuesday of every month. So if you want to get on the mailing list, we do not ask you for anything other than sending you what's coming up. You can actually scan that barcode and sign up on the listserv, and we'll send you a notice once a month to let you know what's coming down the pipe. You can also check out the website to see what's online. But next talk, so April 9th is second Tuesday in April. My friend Ann Paradiso, who actually works in Microsoft Research, is going to talk about her work on technologies that improve and ableism in all kinds of learning and seeing and moving around in real life. So she does some amazing work. So I hope you'll come and check that out. And this is not a talk about AI and how it's taking over your brain. So that's a different, we'll do that some other time. So the way this works is I'll introduce our speaker. He'll give you an amazing talk to knock your socks off. We'll then take a short break. We'll give away some prizes. So if you haven't got a raffle ticket yet, we'll get you one. And then we'll do a stump the speaker question and answer session afterwards. So you can ask him whatever. Now he can not answer your question if you're asking something too personal, but otherwise you can ask him whatever you want. So I should mention, I always forget to do this, the sponsors. So my School of Interdisciplinary Arts and Sciences, the Office of Community Partnerships, who Joel doesn't actually know this because I keep forgetting to tell speakers, he actually gets a small honorarium for giving his talk tonight. That's right. That's right. It's a pat on the back. I hope that helps. And then 7Cs for giving us the space back here and helping us out every month. So thank you all for coming. Without further ado, I'll introduce our speaker and get him set up. So Joel Eklof is a PhD candidate in the Civil and Environmental Engineering Department at UW in Seattle. Joel received a BS in Physics from the University of Puget Sound. It's not very far away. And an MS in Civil Engineering from the University of Washington. Before starting his current PhD project focused on permafrost thaw and accompanying wetland carbon release in Alaska. You can tell the old guy has got to get this longer away from him. Joel can generally be found probing permafrost or teaching science in Alaska, which he'll tell you a little bit about as well, getting muddy on a bike in Swan Creek Park, or playing Match My Pitch with his choir director wife. I feel like that's going to come up in question and answer. If you have too much time in your hands, ask him about waffle recipes, field safety, or why he loves the city of Tacoma. Without further ado, our speaker, Joel Eklof.
Awesome. Thanks, Jim. Thank you so much for having me. Thank you so much for everyone being here, and to 7Cs for having us as well. So yeah, as Jim said, my name is Joel Eklof. I'm a PhD candidate at the University of Washington. And today I'm going to be talking about a little story about a very large donut in Alaska. So to get started, I'd like to acknowledge that this work was done on the traditional ancestral lands of the Puyallup, Duwamish, and Dina-Ina peoples of Washington and Alaska, and I'm very grateful to have been able to do work in all of these places. To start, as many great stories do, we're going to start in the city of Tacoma. And then we're going to take a short trip about 1,000 miles north and 1,000 miles west to Soldotna, Alaska, which is on the Kenai Peninsula down in southern Alaska, and that is where we will find our donut. So we're going to zoom in on our donut. Now, through the magic of both aerial photography and very poor PowerPoint transitions, we're able to increase the detail of our donut. And there it is. There's our field site. There's the subject of our story. So everywhere you see dark green, it's dark green because there are black spruce trees, which do really well growing on permafrost. So those black spruce act as an indicator that we have frozen soils beneath the surface. So permafrost is soil that remains frozen all year round. These are a couple images of what permafrost can look like. The image on the left, I took this photo in the permafrost tunnels outside of Fairbanks, Alaska. That's what is referred to as an ice lens. It's basically a giant mass of ice beneath the surface. Equally being permafrost, our image on the right, we have soil that has ice more spread throughout, but both are permafrost. And of course, we wouldn't probably be here, and I probably wouldn't be studying this if it wasn't for the fact that a lot of that permafrost is making its way out and warming. The globe is warming. In Arctic and subarctic zones, it's warming 3 to 4 times faster than the rest of the globe. With that, permafrost is thawing. Permafrost that has high ice content, when the permafrost thaws, that ice is going to melt. As that ice melts, all of the space the ice once had then collapses, and it will cause the entire surface to subside. And that causes many Arctic areas to have infrastructure damage like this. On the upper right, we have a road outside of Fairbanks, Alaska. The lower right, that is a building in Siberia. So some areas on those figures subsided due to permafrost thaw, while others stayed at a relatively constant elevation. When that happens, infrastructure tends to get ripped apart, as we sadly see in those images on the right. Another consequence of permafrost thaw and subsidence is the formation of wetlands. Wetlands, very intuitively, are areas that stay wet year round. So at our donut, both the inside, we can call it the donut hole, as well as the area outside of our donut are both wetland areas. Wetland areas can look like this. So the image on the left is actually the inside of our donut. The image on the right is sphagnum moss. It's a type of moss that grows very frequently in northern high latitude areas. And as you can see, it's very wet, as we would expect. Wetland formation and this landscape transition from permafrost to wetland are one of the main reasons that we study permafrost science. And the reason is what happens during that landscape transition. So permafrost soils contain a massive amount of the element carbon. Carbon is everywhere. It's in the graphite in your pencils. It's what makes up the diamonds in your jewelry. And everyone here is about 18% carbon. Permafrost soils contain 1,500 gigatons of carbon, which I know means nothing to anyone as well as myself. So I'll say it a different way. Permafrost currently contains twice as much carbon as is currently in the atmosphere. And the majority of the greenhouse gases that we're most concerned about that are causing the greenhouse gas effect and the warming of the globe are carbon-based. The main two are carbon dioxide and methane, CO2 and CH4. So when carbon is in permafrost, it's kind of frozen in place. It tends to be inaccessible to microbial communities. When permafrost thaws, all of that carbon then becomes available to be processed. And when that process takes place, all those little Pac-Man microbes will then release that carbon as either CO2 if we're in an environment that has oxygen, or as methane if we're in a environment that doesn't have oxygen, such as wetlands. So when that carbon is processed in a wetland, it tends to be released as CH4, methane. And the reason we care so much about methane is it is 28 to 35 times the warming potential as CO2 on a 100-year timescale. So it takes very little methane to have a very large warming effect. To make things worse, I swear we're going to turn this around. We're going to talk about a donut. It'll be great. To make things worse, this has caused what we call a positive feedback loop or a self-perpetuating feedback loop. So the atmosphere is warming, especially in the Arctic and subarctic areas. That's causing permafrost to thaw, causing more carbon to be available. That's being released as CO2 and methane, which then adds to global warming, and this perpetuates itself. But I want to be clear that right now, emissions that are coming from permafrost thaw are not our primary concern when it comes to global warming. Human-generated greenhouse gas emissions are massive compared to what we have from permafrost. But permafrost complicates how we handle the climate crisis in a very particular way. So I want to go over that using a bit of an analogy. So Our human-generated greenhouse gas emissions, we can think of as water coming out of the spout. Over time, that the flow rate has increased and increased as we've put more and more greenhouse gases into the atmosphere. Our permafrost is like the pipes underneath that water need to get up there. Because the flow rate has continued to increase and increase and increase, it's gotten beyond the point that the pipes were built to handle. In the same way that as we've continued to warm the globe, it's now causing our permafrost to thaw. In this analogy, we've now started to have leaky pipes. We're going to have these methane emissions. We're going to have these carbon emissions from permafrost thaw. And the part that we really need to pay attention to, and why there's so much research going into permafrost, methane, and carbon right now, is even if we as humans are able to greatly reduce or even get to net zero, we've already started that positive feedback loop. So we're going to continue to have methane and CO2 emissions from the Arctic for decades and decades after we are able to reduce our emissions entirely. The scale of these emissions currently are about on the scale of a top emitting country. So you can imagine a US, a China, or a Western Europe kind of up in the Arctic releasing greenhouse gases. And that's how much we're getting from thaw now. If we continue to warm the globe, that's likely to increase. But even if we completely turn off the faucet, we're going to still have those leaky pipes. Great. So now that we are thoroughly motivated and all in great moods, let's talk about a donut. So here we are back at our donut. So our site is in the southernmost part of Alaska on the Kenai Peninsula. This area is actually very commonly modeled as being permafrost free because it has an air temperature that is on average above freezing. Our site has an average temperature of about 4 to 5 degrees Celsius, which is a little under 40 degrees Fahrenheit on average. So this permafrost exists in a place that is not conducive anymore to its formation. And it exists still due to certain factors that we'll talk about in a bit. So again, this is our site. It was discovered by Ben Jones, who is now a friend and colleague. He has a cabin in the area. He was on a hike and he was like, that's a weird looking thing. I like donuts. And then he wrote a paper about it. And in 2019, we found our way to the site to do new studies on it. So the first question we had is what happened at this site since it was last studied by Ben Jones. And as part of that study, he split the donut in half, that line you can see right across. And he did a permafrost survey, which is measuring depth to permafrost along that entire line. It is a exceptionally technical measurement where we stick a really long piece of metal in the ground. And when we hear a little king, and we feel that we hit something hard, that's where we record the depth of permafrost is. And when that's happening, that's when we're hitting ice. So Ben Jones did a survey in 2015. I repeated the exact same survey once we got to the site to see how the site changed during that time. Here is a figure of that data. So the y-axis on both sides is elevation. The x-axis is distance along that slice through our permafrost donut. You can see a big skip of numbers in the middle. That's skipping the wetland because we have no permafrost in that area. The solid black line is our surface elevation. So as we go in the middle of the donut, it tends to go up, then goes back down as we near wetlands. And then finally, the black line with black cursors, those are the permafrost depths as they were measured by Ben Jones and published in his 2016 paper. So now I'm going to overlay the permafrost survey that I did in 2020. And we saw during these 5 years, from 2015 to 2020, we saw on average 6 centimeters of thaw per year, which in terms of the literature, in terms of permafrost studies, is pretty quick. But then we had quite a surprise between 2020 and 2022 when that thaw rate actually increased 9-fold to 54 centimeters per year, which is just about as quickly as you can find in any study that isn't coastal permafrost or a giant hill erosion event. Everywhere you see gray areas, that's where the permafrost had receded past our frost probe, which I extended all the way to 3.1 meters. And let me tell you, sticking that in the ground 300 times in a day, I don't think I'm physically able to make that probe any further. So I just can't overstate how quick this thaw was, which of course had us wondering, had us asking, why are we potentially seeing this massive increase in thaw in such a short time scale? And our first clues came when we looked at the climate data, the weather data since the site was first discovered. So our left figure is showing snow water equivalent. Snow water equivalent, it's a bit of a back and forth term, but it's the amount of water that snow would have if you melt it at a given location. So we can just think of it as amount of snow. For that left figure. On the right figure, we have cumulative precipitation. The cumulative just means with every rain event, the line gets higher. So the highest lines had the most water in any given year. Now we have a pretty striking result when I overlay the 2020, 2021, and 2022 data, and we see a stark difference compared to those preceding 5 years. We had the 3 snowiest years on record since the site was discovered, and we had 3 of the 4 wettest years on record as well. So that's a big clue. I'm going to end up talking about rain and snow quite a bit, and we'll come back to this to kind of draw some conclusions in a bit. So the next kind of main part of the study, we saw this extremely rapid thaw, but this thaw happened very non-uniformly across the site. So here we are in 2020. Once we hit 2022, we had all of this new thaw, and it happened in different ways across the site. So I'm going to break down our site locations into 3 different categories based on elevation. We have hummock locations with this green background. Hummock locations have the highest elevation. They have the most canopy. Because they have that high elevation and canopy, they have very little snow. It all gets caught in the canopy, and they're quite dry. On the other side of things, we have our hollow locations. Those are the lowest places on the landscape. Because they're so low, all the water flows down to those low areas. They're really wet. They have no canopy, so they have really deep snow. So that hummock and hollow is kind of the opposite of one another. And then in between, in orange, we have our transition locations that tend to be on hill slopes and have values in between in both canopy, elevation, soil moisture, and snow depth. So now I'd like to bring your eye to this box plot in the upper right. Our y-axis is thaw depth, and our x-axis are our 3 different location types. And the big takeaway here is hummock locations thawed much, much more slowly during this same exceptionally rapid thaw 2020 to 2022 event than hollow and transition locations. Hollow and transition locations both thawed very rapidly, around 50 centimeters a year. 50 centimeters a year. And we'll get kind of the next big step is why we see these huge differences in thaw rates across the site. We're going to start with our hummock and hollow locations and get to a point that we can really explain why we're seeing these thaw rates between those 2 different elevation groups. And we're going to do this by looking at 2 different seasons. On the left, we have our warm summer season. On the right, we have our cold winter season. We're going to start with the summer season. I'm going to teach you a term, but I argue you are all already experts on it and you just don't know it yet. So we are going to use the term thermal conductivity. The definition of thermal conductivity is the rate in which heat passes through a material. Great, technical, weird, you're not with me yet, I get it. Here we go, we're going to keep going. And to do that, I'm going to take you to a fantasy land. I call that fantasy land Arctic 7 Seas. It's exactly where we are. It looks the exact same. It's just really cold, and none of us are wearing shoes. Stay with me. Okay, here we go. It's cold. No one has shoes. A stranger, the stranger is me, comes up to you and makes you an offer. Your goal is to keep your feet warm. It's really cold. Would you rather, option A, continue standing on concrete, or would you rather, option B, stand on a mat? Point to which you'd rather have, concrete or the mat. Literally every single person here knows you would rather stand on a mat. Perfect. You're all experts. Mats no longer exist in our fantasy scenario. So the reason everyone chose that mat is because it has a very low thermal conductivity. Energy moves very inefficiently and very slowly through materials like the mat, but very efficiently through concrete. So if you walk into the garage, you have a yoga mat, you have a bit of carpet, whatever, it feels much warmer to stand on that material than on the concrete. They're the exact same temperature. They were both in the garage the entire time. But because energy transfers so much more quickly through the concrete, it's able to take that heat energy from your feet. Perfect. That was part one of a two-part. I'll be right back. Question 2 from the stranger. Would you rather have option A, dry socks, or option B, wet socks to stay warm? Go ahead and point. Everyone says the dry socks. And the reason for that, you didn't know it, but the reason for that is because the thermal conductivity of air is significantly lower than the thermal conductivity of water. And as I was spraying that sock, what I was doing is I was slowly changing the pore space in the sock from air to water. And as I do that, I increase the thermal conductivity. So if I was to be wearing both socks, my right foot would get colder faster because I'm transferring energy more quickly. That principle is the exact same for our hummock and hollow locations. As a reminder, our hummock locations, being on a high point, having all that canopy, having all those black spruce taking in water, they're significantly drier than our hollow locations, which have extremely wet soil and therefore higher thermal conductivity. So when we're in the warm season, we have our wet hollow soils and our dry hummock soils. We expect those warm air temperatures to be able to more efficiently transfer into our wet hollow location than they would be able to our dry hummock location. And that is exactly what the data shows us. We see the maximum temperature reached at a soil temperature of 10 centimeters was significantly higher at our wet hollow location than our dry hummock location. Awesome. Let's make our way to the winter, and don't worry, we're still in Fantasyland. So I learned pretty early backpacking that a wonderful trick to stay warm when you're sleeping is to run around, to do a bunch of exercises, and instantly jump into your sleeping bag. Is that something people have done before? Am I on my own? Is that just me? And the reason for that, we want to have that energy source. We want to have that heat that then we can jump into our sleeping bag and insulate. Because our hollow location has little to no canopy, it has deep, deep snow. Our hummock location, having so much canopy, has almost no snow. So our hollow location is the equivalent of running around when all summer they're being baked in 24-hour Alaska sun. Then the moment we get to the cold season, they're under deep snow, and that deep snow acts as an insulator and keeps all of that energy that the soil gathered throughout the warm season inside the soil, and it's unable to escape from the atmosphere. Our hummock location that has very little snow, though they didn't get quite as warm during the warm season, that's the equivalent of running around, and then you just lay on top of the sheets in a cold room. You're going to get cold quickly because you don't have any insulation. And again, that's exactly what the data shows us. We see our hummock location get significantly colder, on average -3 degrees Celsius, while our hollow location, being under that deep insulation, stays right at about 0 degrees. So putting all that together in review, our hummock location thawed much more slowly, while our hollow location thawed rapidly. It makes sense because our hummock location got cold during the winter and stayed relatively cold during the summer, so it was able to preserve that permafrost better, while our hollow location gets really warm during the warm season, during the summer, and is so insulated during the winter that heat is unable to escape. So it's warm, relatively warm year round, and it's thawing rapidly. And that leads us to our transition locations, which to us were a big question mark because we know they have all of these different variables, canopy, snow, soil moisture, that are between hummock and hollow locations. So we expected thaw rates that would be somewhere between hummock and hollow locations, and that didn't end up being the case. And the reason was that those transition locations were thawing due to a different mechanism. And that mechanism is advective heat transport, which I'll define in a second. So During our study period, we had 2 large rain events, and we define our large rain events as more than 50 millimeters of rain in under 2 weeks. On the right, we have an example of one of those rain events. The top figure, the y-axis, on the left side is air temperature, that red line. We had an average air temperature of around 15 degrees Celsius. On the right, we have cumulative precipitation, and we see we had a bunch of rain during that time. This lower figure is soil temperature from an example transition location. And we see coinciding with the timing of this rain event, this timeline is the exact same for both figures. We see soil temperatures absolutely explode in the middle of that rain event. Not only did we have increases in soil temperature, but we had soil temperature at many depths go from 0 or freezing to above freezing in positive temperatures. Each one of these lines coincide with a different soil depth. The warmer the color, the closer to the surface, the colder the color, the deeper we get. And that coincides with this thermistor illustration on the left. So advective heat transport. What we have been talking about when we talk about thermal conductivity is called heat conduction. So that is the process that heat goes from a hot side to a cold side, and it slowly through an object or through a media tries to reach thermal equilibrium. This is not that. This is a much quicker process. This is transport of heat through a bulk motion of fluid. So we're getting that energy transport through the rain infiltrating through the soil and flowing through the subsurface itself. So we had our example when I had the dry soil and then I sprayed on the soil. Advective heat transport is more like that. I pour my tea in, it's directly going in through that fluid and heating at a much more rapid rate. So those are the clues we have that this is advective heat transport initially, is just how quickly it happened and the timing with that rain event. And the next step was to take example locations like this and see how universal this effect is across all locations. And the answer was it took place at all of our transition locations, all of these hill slope locations with intermediary elevations. The y-axis for these 2 figures, the top is 2021, the bottom is 2022. The y-axis is soil thickness, which warmed from at or below 0 degrees Celsius to any temperature above 0 degrees Celsius. So all of those lines that jumped off 0 on our last figure, those are counted in this soil thickness. And we see both years, we had over 100 centimeters of soil at all transition locations, both years, had that massive warming event take place, while hollow and hummock locations did not. The next big part of this was to try and see if it's actually possible. It seemed like such a huge amount of warming to take place with a moderately small rain event. And we got a lot of questions once we brought this to the field. So we made a model to check it. So this model sets energy that's available for warming and thaw from our rain event to energy that's needed to cause the observed warming and thaw. So energy that's available in the runoff depends on just 2 things: the amount of runoff and the temperature of that runoff. The amount of runoff depends on the ratio of hummock area that water is falling on that will then flow through downhill to that transition location, as well as the temperature of that runoff. Because we don't know the temperature of the runoff, we set that as our y-axis in this figure so that we're able to have lots of different scenarios for what that runoff temperature could have been. The y-axis goes from 0 degrees, which is our permafrost temperature, to 15 degrees, which was average air temperature during that time, which we can use to estimate rain temperature. So we have a very good idea that runoff temperature is somewhere between those 2 extremes. So that's what affects energy to cause warming and thaw. Then we have energy required to have that warming and thaw that we observed, and that depends on a few things. Soil temperature, which we know because we have our soil temperature probes. soil moisture, which we also have from field instrumentation, as well as ice content, which is an unknown. We had no idea how much ice content we had going in. Because of that, ice content is our x-axis. So this model, the simple next thing is to set those two values equal to one another. So along this line right here is when energy available in runoff equals energy necessary to see the observed warming and thaw. Above this line, we have extra energy in the runoff. Below that line, we don't quite have enough energy in that runoff. Now, if I overlay kind of a bit of a more nuanced estimate of what that runoff temperature could have been, we see first off that we have lots of scenarios on and above this line. So it absolutely could be possible that this warming and thaw is due entirely to advective heat transport after rain. But also we see that that's only the case when we have pretty low ice content. So basically any phase change of water, whether we're freezing water, melting water, boiling water, takes a ton of energy. Just think about how long you have to leave a pot on the top of the stove to get it to boil. It's a moderately similar amount of energy to go through the liquid and solid phase change. So because of that, this is only possible if we have relatively low ice content. So now we're going to return, I promised I would, back to that original observation of that 9-fold increase in thaw rates in those especially wet and snowy years. And now everyone knows way more about the effects of wetness and snow on how soil temperatures change. So we think that that huge increase in thaw rates, that 9-fold increase in thaw rates, was likely only possible because the site had low ice content when we began to study it. So we think the site likely looked like this decades ago. This site has continued to experience average temperatures above freezing decade after decade. And during that time, there might not have been a huge increase in depth to permafrost, but we think during that time, we've had a slow reduction in ice content, which reduced the resistance of this site to potential rapid thaw like we saw from 2020 to 2022, such that it was primed for those large events, the snow that was insulating the soil during all of those winter seasons across the entire across-site transect, as well as all of that rain, which both could have contributed due to increased thermal conductivity, which everyone is an expert on, as well as advective heat transport, to then take the site when we found it in this state and get to the rapid thaw that we observed. And with that, just to kind of bring things together and do a quick review, we saw a 9-fold increase in thaw rates during especially snowy and wet years, and we think this was possible due to low ice content from decades of warming. We figured out that hummocks were protected by low snow, so a lack of winter insulation, as well as low soil moisture, which kept them significantly cooler during the warm season. Hollows thawed for the opposite reason, so they had extremely high snow during the winter, which kept them insulated, didn't allow heat to escape from those warm soils during the winter, and their high soil moisture in the summer made it so they very efficiently had soil infiltrate into those soils. Transition locations thawed due to advective heat transport after large rain events, and a bit of kind of an extra way forward. So I mentioned this site is a bit special because it is so south and permafrost still exists. Because of that, this site is experiencing the types of weather that we expect in places like Fairbanks a decade from now, 2 decades from now. So because of that, we had this bit of a view into the future in a way to see how permafrost might respond when we have those more extreme and warmer climate forcings in more northern latitudes. And kind of taking things into account from that lens, we expect that we're going to have an increase in many of these mechanisms, both in frequency and in magnitude in more northern latitudes, as those warm temperatures continue to creep up north, that rainier temperature continues to creep up north, and more extreme rate events are expected as well. So that advective piece is likely going to increase. And with that, thank you so much. Ways to contact me are on the right. And I am pleased to announce that actually this week, the paper showing all the data that I just presented was officially accepted. So there is a pre-proofed version available online. So it's not pretty, but it's all there. Thank you so much, everyone.
All right, we'll give Joel a brief rest, and anybody who has not gotten a raffle ticket, if you could let me know by raising your hand, I will get them to you. All right, in case you're wondering what you're winning, we have some small children that some folks are looking to pawn off. So the first one will go to, so we're giving away hats with the Think and Drink swag on them. Just in time for 60-degree weather, so you can look like a teenager. It'll be great. Or most of my college students. Shit. Old. Uh-oh. Okay. Sorry. Pick thing. All right. First winner is, last three numbers are 936. 936. Anybody? You got it? All right. Awesome. Second one. Okay, let's see what we got. The last three numbers are 906. 906. Hey. All right. If you didn't win, remember, April 9th is our next talk. You can come back and try again. We still have, I don't know, probably enough hats to last us through the end of 2024. And then we'll have to move on to whatever the next thing is. We do, I didn't explain, but we do go through different wear. So we've done shirts, we've done ball hats, we've done socks. Now we've done toques, hoping to not go to underwear. So we'll figure out something else to go next. If you have ideas, let me know. All right. Thank you all for coming. We're going to do some question and answer. So we'll call Joel back up here and we'll take questions from you.
Yeah, absolutely. That's a great question. So yeah, the black spruce especially really impact things in two ways. The first is the snow, which I touched on a bit. And then the second is just the amount of water they uptake. I actually have a paragraph in my paper that is, I like going to magical lands. It's a magical land where there was no topographic change. Everything was flat. And we just had areas with trees and areas not with trees. And in that scenario, I went through how permafrost would thaw in that environment. And the main takeaway is everywhere that has trees, permafrost tends to stay because they lack that snow insulation, because the soils are drier, where all of the areas without trees will continue to thaw. And then we kind of end up with a site like we see. We have these big topographic differences as subsidence takes place. And then those transition locations, those slope locations, cause the high points to kind of be cut into. So the last things will be left are those trees. So they're absolutely massive. And kind of one of our main takeaways are that the black spruce, at least in this type of scenario, are controlling a massive amount of things. We also looked at terrestrial vegetation and moss depth. Those didn't end up varying significantly between our groups and also didn't make a massive difference on soil temperature. So they didn't make it into the presentation. But yeah, that's a really, really great question. Thank you. Yeah, Dan. Yeah. So there is one of my favorite science terms is drunken forest. And you can actually see it on this figure. So when we have moderately dry soils, when we have permafrost underneath, the black spruce grow straight, grow tall. As the permafrost begins to be eaten away, those soils get wetter and wetter without that canopy. And the soil saturation gets too high, such that the black spruce just start falling over. And there's always a massive amount in that kind of intermediate stage of just kind of leaning both ways. So when you look at a permafrost landscape, especially in warming environments, which is sadly a lot of them now, you'll get to this area between a wetland and a permafrost plateau where you just have dead trees, then leaning trees, then slightly leaning trees, then alive trees. And that's due to them basically getting flooded out and not having enough oxygen. One other kind of interesting thing about black spruce, you can tell how deep the permafrost is based on how large the black spruce are. So when you're at areas with really tiny black spruce, they tend to be really, really cold and have shallow permafrost because the roots can't grow into permafrost. The depth of the layer that thaws every year is the depth that's available for roots. So as you go to slowly deeper and deeper permafrost, you tend to have larger and larger canopy just because there's more room for roots. Yeah. Yeah, that's a great question. So, a lot of work, especially kind of in more northern areas where there's a ton of oil, the thawing of the permafrost as well as low snow conditions have made accessing those sites way both more difficult and impactful. So, because the soil is just becoming softer without the support that is permafrost, and because there's lower snow, Matthew Sturm is a professor at the University of Alaska Fairbanks. He's done a lot of work on having to now collect a ton of snow and build snow roads to get to different rig areas, when before you wouldn't have to. You would just have rigs where you're just on snow on permafrost. We now have all of this infrastructure, all of this extra time, all of this extra money to be able to safely and without a massive environmental impact get to those areas. So yeah, awesome question. Yeah. Yeah, y'all ask great questions. So I'll repeat the question. So the question was, as we have this positive feedback loop, as we have permafrost thaw, and in this study, I showed the top of the permafrost table going down, if that's indicative to the permafrost being completely gone at the site or not. And at our site, so Ben Jones, when he studied the site in 2015, did what's called coring. So there are kind of these big rigs that you can bring in, you drill into the permafrost, and it takes out like a really fine cylinder of all of the soil in the subsurface. And from that, you're able to measure the bottom of the permafrost table in a way that I never could with the frost probe. At this site, the bottom of the permafrost table is around 6 meters. So at some locations, especially those that we can visually see when they become wetlands, that's indicative of the permafrost being entirely gone. But many of these areas that I've been showing that have had that top down thaw, they're also likely thawing from the bottom up. Being connected to wetlands all around, there is now groundwater flow underneath the permafrost as well, likely. So that's likely condensing from both directions. Is it gone in some of those locations? Likely, but I don't really have a way to tell. If you go far north, you can have 200-foot thick permafrost. When you have these really cold environments, kind of the bottom threshold of the permafrost table is when you get into like geothermal warming type of areas, that type of depth. And then when that's kind of competing with those extremely cold atmospheric temperatures. Yeah, of course. Yeah. Yeah, that's a great question. So, compared to many, this is extremely fast as far as permafrost thaw goes. We probably have centuries. There are also some areas where permafrost is actually increasing. For many of the reasons, this site still existed because of the canopy, because of the topography, because of these things that are able to protect the permafrost. If you have those things in an area that is, 5 to 10 degrees colder, you can actually be increasing your permafrost in some areas. In terms of when we'll have a time where we have a net increase in permafrost thaw, We gotta go down a few more degrees, which is not really on the docket for now. But yeah, yeah. Yeah, that's a great question. So, permafrost is just soil at or below freezing. So that can mean a massive different things. So, like for example, glacier tends to be very strictly snow that compacts, becomes ice. Now, glacier. Permafrost, on the other hand, can be lots of different things. So, at this location, it's entirely peat, which is a soil type that's partially decomposed organic matter. So, over the last thousands of years, trees grew, moss grew, it died, it became a part of the soil, it froze, it grew again, it froze, and that happened over and over again. And that led to the depth of peat that we have and this frozen amount of soil. There are other areas. Permafrost can be a giant rock in the ground. Permafrost can be entirely ice. It's just soil, which is a very broad definition, that is frozen and remains frozen. Yeah. 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 So the question was how, from kind of a construction standpoint, are we dealing with all this permafrost thaw? There are kind of a few main strategies. One that's almost universal because it's so cheap is they'll just put massive amounts of insulation above and below the foundation of all the buildings itself, just to try and not have the building itself bring heat into the subsurface. So you're almost insulating from the building itself. There's also passive cooling coils, which some of them work different ways, but kind of one way they can work, they're kind of metal structures that go above the snowpack in such a way that those really cold winter temperatures are able to travel down that exceptionally high thermal conductivity metal piece and make its way into a subsurface to cool the soils more than they would be able to naturally. So a lot of the time you'll have that massive amount of insulation and then you'll have passive coils around. But also a lot of building is just moving away from permafrost areas. I've spent now, I don't know, coming up to a year and a quarter in Fairbanks, and all of the locals know which neighborhoods are on permafrost and which aren't. And that changes the real estate market. A lot of people are trying to move to a different part of town because of that. Because all of these strategies that we employ are slowing things, basically. We don't have a, no longer warming future in sight yet. And with that, we're trying to engineer things for 100 years down the road. But we never really know how much is enough. And that kind of depends on, how the future goes. So
what was it like doing field work in this part of Alaska?
Yeah. So the question was, what was it like doing field work in this part of Alaska? It was so beautiful. I should have just added more photos at the end, but we had a time lapse camera that just took a random photo at a certain time every day. There were moose in the middle of the donut hole. There's just a beautiful mountain range across the wetland once you leave the donut. I was allergic to a certain type of fly that was at the site. So one year when I did the permafrost survey, which is a very physical day, I got bit 4 times. And my hand blew up to 3 times the size. And I just put a leather glove on. I left it on the whole day because I was the only one who could do that data collection. And I just had the worst work day of my life. But we got that data, and that was slide number 7. Yeah. Yeah, that's a great question. So it's if the earthquakes have an impact on the permafrost, and that I actually don't. That's not something that I've explored much. I could kind of make wild guesses, um, but the earthquakes will probably open up pore space in the subsurface, which next time water comes around will likely become things like those ice lenses that we saw in the permafrost. But I don't know if there's a correlation with increased thaw rates and increased seismic activity or that kind of thing. That's a really good question. Yeah, so that was great. That was a question kind of about all the complexities around the advective heat transport and how we kind of knew what was happening. So we had soil moisture sensors at all of those locations, as well as pressure transducers at all lowland and hummock locations. So we were able to track the pulses of water through changing soil moisture and changing soil temperature. And kind of from that timing, we were able to track those temperature differences along with those pulses of water. And then the kind of model I showed was for the most conservative volume of water. So we had that was a 2-to-1 ratio of contributing to receiving area. That went up to 6-to-1. So we saw much larger energy pulses, and those were quite easy to track just because of the magnitude of them in those scenarios. I think I saw one more. I want like a really hard hydrology question. What? Yeah. Yeah. Mm. Yeah, so a couple great questions in there. So I'm going to teach one more term to kind of go along with what we were talking about. So we have the permafrost, which the technical definition is at or below 0 degrees Celsius for 2 or more years. We also have the seasonally frozen layer, which we get all over the place. We get it in Western Washington sometimes when we have a really cold day. We'll have this kind of micro layer of frozen soil. That's, of course, not permafrost because it thaws at 8 in the morning that day. But sorry, what was the other? I felt like I had a train and then I. Is there in between? Oh. Yeah, what's the average temperature? Oh, yes. Yeah, that's a great question. So the question was like, what is the air temperature you need to start building permafrost? There are some really interesting wild papers showing permafrost forming at average temperatures of positive 3 degrees Celsius and actually degrading at negative 20. And that just kind of leads to the massive impact of these ecological factors, the canopy you have, the moss you have, the type of soil, the hydrology of the site. So it is a super complicated question. I would say in general, you have to be a good bit below freezing on average to start actually getting meaningful formation. I think it's moderately uncommon above like -3. You start to kind of Fairbanks, where I work, is currently -1, and we're seeing pretty steady thaw. So yeah. The question was kind of about how we're seeing climate forcing vary regionally and how we see those changes, if that might change where we see permafrost, where it's thawing, where it's forming. And absolutely. Those one kind of big driver. So we have the length of the winter is a really big driver. just how cold those soils get, because that's where the formation really happens. And then as we get to the warm season, if it's able to stay cold enough, then we begin the formation of permafrost. The kind of big thing that is arguably more important than the duration of the winter is the duration of the snowpack. A lot of these areas, we have many areas that are having winters and snowpacks that have differing patterns that are happening. Things are very complex all over the place. Kind of the golden scenario is a long winter with less snow in terms of permafrost. But of course, in terms of water resources, in terms of salmon recovery, everything is kind of a give and take in that way. But those longer, colder winters, if they have low snow, that's often what is able to kind of begin creating those formations. And like you were talking about the East Coast and the Midwest of kind of the contiguous US, a lot of what we're thinking about as well is, Eastern Canada, these areas that do have those colder average temperatures already, as well as Fairbanks, as well as all these areas. Everywhere is having these vastly changing seasons that sometimes have patterns and a lot of the time don't. My site in Fairbanks in December of 2020, we saw half of the year's rain fall in the middle of December. There was a meter of snow. We had this massive rain on snow event. Soil temperatures are much colder there. So a lot of my locations are down at -10 degrees Celsius and went straight to 0 in the middle of December when we had this huge rain on snow event. So we expected mass thaw, and then it was a dry summer. Thermal conductivity was low and nothing really happened. And we have all of these complications that are adding to one another and taking away from one another. So lots of complexity in every direction, but those seasonal changes are being talked about all the time. Yeah, great question.
Thank your speaker one more time. Yep. Thanks, Joel. You're welcome to hang out for a little bit. They usually like us to move out into the main space, so they keep an eye on you people. But if you have beer glasses and stuff, there's usually a spot back here where you can put that stuff. That would help me out. Otherwise, I have to clean up everything. So thank you all for coming. Hopefully, we'll see you in April.